The first thing in the question, and it's in bold, throughout this question use g equals 10 meters per second squared. If you don't read the question thoroughly, you're going to spend ages trying to get the results that you should get. A light elastic string has a natural length of 1.25 meters and modulus of elasticity 25 newtons. A particle P of mass 0.5 kilograms is attached to one end of the string. The other end of the string is attached to a fixed point A. Particle P hangs freely in equilibrium with P vertically below A. I'm going to deal with that situation before I go on and do any of the rest of the question. So, what I've got here is my point of suspension, and I've got my particle hanging down here, and its mass is 0.5, so therefore we've got 0.5 g force that way, we've got tension that way, and this is our situation at equilibrium. In other words, T is equal to 0.5 g. And we know the natural length is 1.25, so in this position, this distance is going to be 1.25 plus what I'll call E for extension. So as just mentioned, equilibrium, T is equal to 0.5 g. Now, the tension is equal to lambda x over L. So here, that is going to be 25 E over 1.25. That's going to be equal to 0.5 g, and that gives us the extension is 0.5 times 10, remember in this question, times 1.25 divided by 25, giving us that E is 0.25. We're now told the particle is then pulled vertically down to a point B and released from rest. Show that while the string is taut, P moves with simple harmonic motion with period pi over root 10 seconds. So what we want to do now is look at the next step. So we're pulling it down from its equilibrium position. And so if we say the equilibrium position is just there, and we can say while it's in this motion, it's got a distance x from there. So we'll have a tension here, and of course the mass still exerts a force downwards of 0.5 g. So in this position, it would be accelerating upwards like this. And note the acceleration would be in a different direction to that in which we're measuring the extension. So T take away 0.5 g is going to be equal to negative 0.5 a, and that's to do with the acceleration being in the opposite direction to the extension. So in this situation, we've got lambda e plus x divided by the natural length of, well, let's just call it L for now, and we'll substitute in a moment. Take away 0.5 g is equal to negative 0.5 a. And so let's substitute in what we know, 25. This one is going to be 0.25 plus x divided by L. Take away 0.5 g is equal to negative 0.5 a. So we have 25 0.25 over 1.25 plus 25x over 1.25. Take away 0.5 g is equal to negative 0.5 a. But we know that this and this will cancel out. That's the equilibrium position. And so we just have 25x over 1.25 is equal to negative 0.5a. And rearranging, doing a bit of calculating, gives us that a is equal to negative 40x. So that's an x double dot is equal to negative k squared x. And that shows SHM. Not only that, but we can see by comparison that k is equal to root 40. So the period of the motion is 2 pi over k for SHM. So that is 2 pi over root 40. That gives us 2 pi over 2 root 10, which is pi over root 10 seconds as required. The maximum kinetic energy of P during the subsequent motion is 2.5 joules. Show that AB is 2 meters. Now, I can't find it on the formula booklet, but once we know we've got SHM, there is a formula, V squared equals K squared, A squared minus X squared. And we know that the max speed occurs when x is equal to 0, so when it's at the equilibrium position, so at equilibrium. And that maximum speed is v is equal to ka. So v would be equal to root 40a, since we found that k was root 40 earlier. So the maximum kinetic energy of 2.5 is going to be a half times the mass times v squared. And so we can calculate from that v squared is equal to 10. If we substitute back to here, we get root 10 is equal to root 40a. And that gives us that root 10 is equal to 2 root 10a, giving us that a is 0.5. So if we now think about a diagram from the point of suspension, we know that the natural length of the string is 1.25. The equilibrium position is an extension of 0.25. And now we've just worked out that the amplitude of the motion is a further 0.5. And so overall, that distance is 2 meters. The particle returns to B for the first time t seconds after it was released from rest at B. Find the value of t. Now, it's going to become slack. The string's going to become slack there. And then it's going to have free motion for this part. So it's going to do SHM in this region here, and then free motion for the part up there. So, once again, we can use v squared is equal to k squared, a squared minus x squared. So v squared is going to be 40. 0.5 squared, take away 0.25 squared. And that gives us v is 2.7386. So that will give us the speed at this point where it becomes slack. Then we're just going to use a suvat. So we know the U is 2.7386. With no resistance on the way down, when the string becomes tight again, it will be negative 2.7386. The acceleration we know is negative 10. And the time is what we're trying to find. So we can use v equals u plus at, and we'll have negative 2.7386 is equal to 2.7386 take away 10t, and that will give us that t is 0.5477. So this is the free motion part, and then we know that x is equal to 0.5 cos root 40t is a way of expressing the x, and we know the string becomes slack at 0.25. So if we put negative 0.25 equals 0.5 cos root 40t, and we can solve that on our calculator, we'll find that the time for that, which I'll just call t prime, is 0.3312. And so the time that we want is going to be 0.3312 times 2, because we've got while it goes upwards here and then while it comes downwards, plus the free motion time. And that is 1.21 seconds.